Number Theoretic Functions Part 6. The greatest exponent of a prime dividing n factorial. In Part 6, we discussed the greatest integer function and its applications. The greatest integer function of x, box x, takes in a real number x and produces the greatest integer less than or equal to x. It is the unique integer satisfying the inequality x minus 1 strictly less than box x less than or equal to x. First, we look at the greatest power of a prime that divides n factorial. Before going any further, we claim that it is given by the formula the sum as k goes from 1 to infinity of the greatest integer of n upon p to the k. If we wish to calculate the greatest exponent of p dividing n factorial for an arbitrary n prime p, we first study the numbers 1, 2, 3 all the way up to n that multiply together to produce n factorial. Some of these numbers are not divisible by p while others are. Of those there are, some are divisible by one factor of p, some by 2, some by 3 and so on. In order to compute the greatest power of a prime that divides n factorial, we need to add all the exponents of the prime powers of p dividing each of 1, 2, 3 all the way up to n. To do this, we note that there are precisely box n upon p such numbers that are divisible by p amongst 1, 2, 3 all the way up to n. There are box n upon p squared divisible by p squared, box n upon p cubed divisible by p cubed, and so on. Remember that box n upon p to the k doesn't give us the value of numbers that are divisible exactly by p to the k and not p to the k plus 1. It only gives those that are divisible by at least p to the k. For all we know, there may be some that are divisible by p to the k plus 10 and p to the k plus 12 in box n upon p to the k. Also note that those that are divisible by p to the k need to be counted exactly k times, not more and not less, in the sum of exponents as they each contribute a factor of p to the k exactly. To do this, we need to switch from considering those that are divisible by at least p to the k to those that are divisible by exactly p to the k and not p to the k plus 1. This requires the simple observation that out of the box n upon p to the k numbers that are divisible by p to the k, we need to remove those that are divisible by p to the k plus 1, which is box n upon p to the k plus 1. Therefore, there are box n upon p to the k minus box n upon p to the k plus 1 such numbers that are divisible by exactly p to the k and not p to the k plus 1. This number has to be multiplied by k as each of these numbers are contributing an exponent of k to the overall power of p dividing n factorial. Taking the sum over the infinite possible values of k, we have the sum as k goes from 1 to infinity of k multiplied by the box value of n upon p to the k minus the box value of n upon p to the k plus 1, which should result in the greatest power of a prime dividing n factorial. Simplifying, the sum as k goes from 1 to infinity of k into the box value of n upon p to the k minus the box value of n upon p to the k plus 1 equals the sum as k goes from 1 to infinity of the box value of n upon p to the k plus k minus 1 into the box value of n upon p to the k minus k into the box value of n upon p to the k plus 1. This breaks down into two sums. The sum as k goes from 1 to infinity of the box value of n upon p to the k and the sum as k goes from 1 to infinity of k minus 1 into the box value of n upon p to the k minus k into the box value of n upon p to the k plus 1. But to our good fortune, the second of these two sums reduces down to 0 as it telescopes. The expression in the summand is of the form f of k minus 1 minus f of k, where f of k equals k into the box value of n upon p to the k plus 1. This gives f of 0 plus f of 1 plus f of 2 and so on minus f of 1 plus f of 2 plus f of 3 and so on, and it simplifies to f of 0, which is 0 into the box value of n upon p, which equals 0. Only the first sum remains, which matches what we claimed in the start. Hence the finite sum as k goes from 1 to infinity of the box value of n upon p to the k, which equals the box value of n upon p plus the box value of n upon p squared plus the box value of n upon p cubed and so on, evaluates correctly the greatest power of a prime dividing n factorial. Every number less than n and divisible by p to the k and not p to the k plus 1 gets counted exactly one time each in box n upon p, box n upon p squared, box n upon p cubed and so on all the way up to box n upon p to the k. Therefore it gets counted k times and the finite sum counts the greatest exponent of a prime that divides n factorial. Note that it is finite since there comes a time when p to the k is greater than n, and so the box value of n upon p to the k equals 0. Using what we have learned, we can express a formula for the factorial function for whole numbers that goes by the name of the Legendre formula. It simply is the product of the greatest prime powers that divide n for all primes. N factorial equals the product over p prime of p raised to the sum as k goes from 1 to infinity of the box value of n upon p to the k. With the power of the greatest integer function unleashed, we can now use it to show that the binomial coefficient n choose r is a whole number for all n and r in n union 0 and r less than or equal to n. We prepare the proof with the observation that for any two real numbers a and b, the box value of a plus b is greater than or equal to the box value of a plus the box value of b. With this out of the way, we are now ready to begin. Recalling the definition of n choose r, which equals n factorial upon r factorial into n minus r factorial, we calculate the greatest exponent of a given prime that divides the denominator. Taking r factorial and n minus r factorial, we find that it is equal to the sum as k goes from 1 to infinity of the box value of r upon p to the k plus the sum as k goes from 1 to infinity of the box value of n minus r upon p to the k. However, seeing that r plus n minus r equals n, we fall back on the inequality we established a few seconds ago. This yields the sum as k goes from 1 to infinity of the box value of r upon p to the k plus the sum as k goes from 1 to infinity of the box value of n minus r upon p to the k is less than or equal to the sum as k goes from 1 to infinity of the box value of n upon p to the k. But the expression on the right hand side of the inequality is precisely the greatest power for prime that divides n factorial. Hence, for all primes p, the greatest power dividing the denominator is less than or equal to the greatest power dividing the numerator. Hence, it is always the case that the denominator divides the numerator, and what we are left with is a whole number as our answer. We can take this a step further and show that any product of r consecutive whole numbers is divisible by r factorial. To show this, we translate the problem into algebraic terms by letting the greatest number in the product be n. Hence, the product can be transcribed as n into n minus 1 into n minus 2 and so on, all the way up to n minus r plus 1. This is equal to npr in the case that the smallest of these numbers is positive. But we recall from combinatorics that npr equals ncr multiplied by r factorial, and we just showed that ncr is a whole number for all r less than or equal to n. Hence, the relation npr equals ncr multiplied by r factorial states explicitly that r factorial divides npr, or in other words, r factorial divides the product of r consecutive whole numbers. With this complete, we move on to the last video where we discuss an application of the greatest integer function in the context of other number theoretic functions. In particular, we will be proving the formula the sum as n goes from 1 to capital N of capital F of n equals the sum as k goes from 1 to capital N of the box value of capital N upon k multiplied by little f of k, whenever capital F of n equals the sum of little f of d over the divisors of n. In conjunction with the Mobius inversion formula, this will be the second bridge connecting capital F and little f. The credit for the theory and the proofs goes to David M. Burton, who is the author of the book Elementary Number Theory. Credit is also given to McGraw-Hill Education India Private Limited, who have published the Indian edition.